whistle, and a cup of water. So I've got this cheap whistle, and it's an open pipe. I know it's an open pipe because it's that's the definition of an open pipe. So I've got an open end here, and then this part here below the mouthpiece, that little opening there, that constitutes the other opening. It's called a fipple. So when I use the word fipple, you'll know I'm always talking about the little opening just beyond the mouthpiece. So right now it's an open pipe. However, I'm going to put it down in the water, and now it's a closed pipe. In fact, it's a short closed pipe, because the top of the water, where the water is now, inside the pipe, that stops the wave. So I've got a short closed pipe now, longer open pipe when I take it out. Question?
Well, I guess I'll just wait.
Yeah, why don't you wait? So this is my proposal. I'm going to blow into the whistle, and as I blow into the whistle, I'm going to slowly let the whistle rise up through the water. And then, at one point, it'll go from being just under the water to just out of the water. And in that instant, it'll go from being a closed pipe to an open pipe. So two things are happening. The closed pipe is getting longer, and then the closed pipe becomes an open pipe. So now thinking about the physics of closed pipes and open pipes, can you make a prediction for what you're going to hear throughout that whole process? Elliot?
Well, once you leave the water, it's going to be a little
Before I leave the water, as I'm lifting it, will the tone change?
Yeah, definitely. If it's longer, it's going to be lower. So it's going to. So if you're making it longer by pulling it up, it's going to get lower.
Okay. So he says, as I raise it up through the water, since the column of air is longer and longer, the equation, that L is going to get bigger and bigger, so that frequency should get smaller and smaller. Okay. What about when I actually move it from inside the water to outside the water?
It'll get higher and louder because.
Let's forget about loud. Why would it get higher?
Because it's going from like a huge impedance in the water.
No, you're missing something. It will get higher, but why? Mr. Porter.
Because for closed pipes, there's a 4 in the denominator, but for open pipes, there's a 2 in the denominator. So
he was excited about saying that, I could tell.
Yeah.
He had the smile on his face. I know it.
That tripped me up.
Okay, did you hear it? When I come out of the water, the only difference in these two equations is that number. And so that 4 instantly becomes a 2. Okay, how much is it going to get higher by?
It's going to double.
Okay, what interval is that? What musical interval?
A harmonic. Overtone. Mode. Multiply.
An octave. It'll be an octave higher because it'll be twice the frequency. Okay, so this is our proposal. As I'm pulling it up through the water, L gets steadily longer, frequency gets steadily lower. As soon as I get from inside the water to outside the water, the 4 becomes a 2, and instantly it goes up by an octave. Let's see if that works.
Yeah.
You catch that?
Yeah.
But so is it getting higher as you're pulling it out and then
No, it's
much
getting
higher?
lower.
It's getting lower.
It's getting lower, but at the instant it leaves the water, it becomes an open pipe, and it pops up an octave. So I really like this demonstration. It's so simple, but it really forces you to think about the connection between pitch and length, and it shows the difference between what that 4 does to a closed pipe compared to what the 2 does for an open pipe. Remember I said for the same length pipe, a closed pipe is half the pitch of an open pipe. Gene?
It's trombone.
I think I figured this out, but so the end of the pipe, so that the whole, the fipple,
That's one
so
of them.
that's where the sound comes out.
Yeah. Okay, so that's demonstration number 38. And we're going to skip over 39 because it's a little bit longer, but you should leave